So if I wanted to prove that they were exactly the same, or that they weren't exactly the same, what could I do to this and to this to maybe show that they were the same or not the same? Simplify them, yes. So simplify Tanya's and simplify Alex's and see if you get the same thing. Okay? Simplify the two and just see if they're equal. See if they're the same. Look at Tanya here. We've got 4n squared plus 2n plus 1 times 2n plus 1. That gives me 4n squared plus 4n squared plus 2n plus 2n plus 1. For a grand total of 8n squared plus 4n plus 1. Alex has 4n minus 1, plus 1, minus 4n, 2n plus 1. Alright, so if I square this, I'm going to get 16n squared plus 8n plus 1 minus 8n squared minus 4n. 16n squared minus 8n squared is 8n squared. 8n minus 4n is 4n, and there's nothing for the 1. Are they the same? Yeah. Right here? Remember, that's addition. That's 4n plus 1 times itself. You don't distribute that square, you multiply it times itself. Yeah. Are you writing? Do I need to give you a second? I am not doing these with you, but before tomorrow, I want you to define these three terms. And they're in section 1-3 in your book. They're in bold letters, dark, heavy letters. You can find them and define them. I'm not doing those with you. But I do want to look at some of these together. Okay, this one's done for you. We'll talk about it first. Determine whether the functions are equivalent. Okay, so I have a function that's a table and a function that's a graph, and I want to know if they're equal to each other. Okay? How can I tell if this is equal to that? Right, see, these are points. Like, if these are equal, 1, 11 would be a point on this graph. Well, look, there's 111 right there. 219 would be on this graph. There. 327. Bingo. Alright, so they're equivalent because the inputs and the outputs match. This chart matches this graph, so they are equivalent. Okay? Let's look at number 3. I didn't get a chart for number 3. What did I get? I got an equation. Okay? So how can I tell if this equation matches this graph? Exactly. Substitute it in. Like if I put in 0, let's see, that's 2. If I put in 0, I should get 1. Okay? What happens when I put in 0 into this problem? You get 1. Okay, so this one checks out. I'm going to put a green dot on it because it's good. If I put in -1, what am I going to get? Not -1, sorry, +1. What am I going to get? I should get a -5. Do I get -5? Put that in. I'm going to get -5. 1 minus 7 plus 1. that -5? 1 minus 7 is -6, plus 1 is -5. So that one checks out, okay? What about 3? Does 3 check out? 3 should be -11. Is it -11 when I put in 3? Let's see. 3 squared minus 7 times 3 plus 1. 9 minus 21 plus 1. What's 9 minus 21? -12. And -12 plus 1 is -11. Alright, so that one does okay. Here's the thing. I don't think we need to test every single one of these, but I do think it'd be a good idea to test at least one more on this side, because this could be the kind of graph that goes like that. So I would at least test something over here. So pick a point on this part of the graph, test it in that equation, and see if it works out.